Okay, good evening. This is Professor David J. De Los Reyes. It's January 4, 2023. Okay, my new topic for tonight will be lesson number DE45 under the subject matter second order differential equation. It is still under the application problem. The type of problem is still under oscillatory motion. Oh, this will now be example number 2, another variation of an oscillation problem. Okay, I will try to read the problem for tonight. Okay. A cubical block of wood, 1 foot on a side, and weighing 31.2 pounds, is submerged in still water. The water is not moving, okay? Still water. Until its top surface is in line with the water surface. It is then released. Find the amplitude and frequency of its motion. Okay, the problem is something like this. We are given a block of wood. The dimension is 1 foot by 1 foot with respect to the cross section, and the height is still 1 foot. And this block of wood, the weight is 31.2 pounds. Okay. This block of wood is submerged in still water. This is the water surface. Still water meaning the water is at rest. It is not like a flowing water, right? So it seems it's just the water is in a container. Then we try to submerge a block of wood until the surface of that wood, okay, coincides with the surface of the water. Then after submerging, the block of wood is released. Assuming that the block of wood maintains its vertical upright position at any moment in time, the problem is asking what will be the amplitude of the motion and what will be the frequency. Amplitude meaning if the block of wood tries to rise up, then it tries to go down, it is actually oscillating. And the rise up and going down, that is termed to as amplitude. So the problem is asking for the amplitude. What will be the amplitude? And what is the frequency? So to solve the problem, we must have to compute for S as a function of time. What is S? S is actually the submerged portion of the wood with respect to the center line. Okay? Taking the water surface as the reference. So this S here, as at any moment in time, is variable. As it moves up and down, this S is variable. Okay? This S here is variable. So at any moment in time, the time is also variable. So this is variable, the time is also variable. So we must have to compute for S as a function of time. And to solve that one, we need our knowledge of differential equation. Okay, let's try to bring out it is something like a free body diagram. If we try to submerge the block of wood, whether we like it or not, there will be a force at the bottom, okay? And that force is actually referred to as F, capital letter F, with the subscript B, meaning it is the buoyant force. Buoyant force is equivalent to the volume of the water that is being displaced. Okay? So if you try to submerge the block of wood, there will be a volume of water that is displaced. and the equivalent of that buoyant force is actually equal to the so-called volume of the water displaced. And to compute for the volume of the water displaced, that will be a problem. That's why we study mathematics, okay? So before I will bring out the solution, I will make the representation. I will let S equal to the distance from the water surface to the center of the block. This one. The variable distance from the water surface with respect to the center of the block at any moment in time is represented by S. On the upper figure, I put a negative S. Why negative S? It is below the water surface. Negative S, right? So as the block of wood rises up, okay, rises up, that S with respect to the water surface in the centered line is plus S. So this is for the downward motion, this is for the upward motion. I place the designation of minus S and plus S. For the downward motion, this is minus S. For the upward motion, this is plus S. Because our reference is actually the water surface. Then I will place a capital letter F with the subscript B equal to the buoyant force. And under the study of, it is something like a fluid mechanics. The buoyant force is actually equal to the weight or volume displaced. If we displace the water, the equivalent buoyant force is actually equivalent to the volume of that water. So we need the so-called density of the water to compute for the buoyant force. Okay. The given is the weight is 31.2 pounds. For water, I will check my camera. For water, the density or specific weight of water is actually 62.4 pounds per cubic feet. 1 foot by 1 foot by 1 foot, if we try to consider water, that is equivalent to 62.4 pounds. So I will try to repeat the requirement, the amplitude, and the frequency. Okay, let's try to bring out the solution. To compute for the buoyant force, this is an easy money under fluid mechanics. This is fluid mechanics is something like a fourth-year subject matter, right? So our subject matter for tonight is differential equation in combination with fluid mechanics, because buoyant force is actually density times volume. The buoyant force acting on the block of wood as we try to submerge it is actually equivalent to the density times the volume submerged. This B here is the volume submerged. It should be with the subscript S. And the volume submerged is actually the area times the variable distance S. So actually, the area is 1 by 1. Okay, that's area. And the volume submerged at any moment in time is actually variable. It depends on the value of S. Because for the meantime, S is variable. So this is times S. Okay, 3 dimensions. Volume is the product of 3 dimensions. It should be the length times width times the thickness. But for the meantime, we will just represent volume in terms of S. So the buoyant force in terms of S is actually 62.4 times the quantity, 1 by 1 times S. The product 1 by 1 by S is actually the submerged volume. So the submerged volume in terms of S now, okay, it's a representation. It is 62.4 times S. This is the buoyant force. And using one of the formulas under Newton's law, that is force equal to ma. Okay. The capital letter F on the left hand side is actually the buoyant force. So we will equate this value, capital letter F, we equate that to FB, and this should now be equal to 62.4, okay, S. But this F here is actually against the motion, so I forgot to place this one. This should be, there is a negative sign over here. If the motion is actually downward, the force acting on the block of wood is actually upward. It is against. So this is negative, right? That's the only force acting on the block of wood as we try to submerge it. Okay? It is only equivalent to the buoyant force. And this should be equal to mass is actually weight over gravitational acceleration times acceleration. Acceleration is actually the variable distance here, or the variable displacement of the movement is actually s. So this should be d square s over dt square. And if we try to manipulate this equation here, we place this one on the left, then we try to remove this w over g as a coefficient of this. So we will multiply all the terms by the reverse of this. It should be g over w, right? Because the right hand side times g over w, this g here cancel with this, and this w here cancel with this. Then we try to rearrange, we put this one on the left. So this will now be, the coefficient now will now be unity. It is just only one because it cancels, right? So d square s over dt square plus this 62.4, we put it on the right, then we try to rearrange this, so this will now be plus 62.4. And since we multiply all the terms by g over w, this is now multiplied by the quantity 32.2, the gravitational acceleration under the English system. That is 32.2 feet per second square, or over the weight. The weight is actually 31.2 pounds. So this 62.4 as a coefficient should be multiplied by the ratio 32.2 over 31.2, close quantity times s equal to 0. And if you try to use your calculator, this portion of the coefficient will just become 64.4. So the resulting second order differential equation, that is SODE, will be d square s over dt square plus 64.4s equal to 0. So to find for the equation of the motion, okay, we need to solve this one. And we know how to solve a second order differential equation. There are three cases, right? Real number in unequal, real number in equal, and the third case is actually the worst case scenario, the one we are solving now. If the roots are complex numbers, meaning if that a real part and imaginary part, it should fall under case number 3. Okay? So what will come out? Under second order differential equation, we let s equal to k e raised to mt. ds dt will be km e to the mt. d square s over dt square equal to, you differentiate again this one, this will be km times m, it will now be km square e to the mt. Then we take this second derivative, and the value of s, we put it here. So substituting, it will now be equal to km square e to the mt plus 64.4 k e to the mt equal to 0. There is a common factor k e to the mt. So if we try to multiply all the terms by, we want to eliminate that one, right? 1 over k e raised to mt. Okay? First part, this will disappear. What will come out will just be simply m square. Second part, okay, this will disappear after the multiplication. So it will just be simply 64.4 equal to 0 times 1 over this will still be 0. Luckily, some part of the quadratic equation is missing, so actually we could now compute for m after the transposition. And m square equal to minus 64.4, right? Then try to raise both sides of the equation to the 1/2. Loss of exponent, SAT shorts video, right? M squared raised to the 1/2, this two here cancel with this, right? So M now equal to, this is negative 64.4. So we can write this one, square root is just the radical sign without the 2. If the 2 is missing here, it is understood to be square root. Negative 64.4 can be written as negative 1 times 64.4. And we will replace this negative 1 by the value of g squared. So g squared is a perfect square. 64.4, we can take the square root of that. So the value of n now will be plus or minus, the square root of g squared is just j, and the square root of 64.4, it is plus or minus. That's why this is preceded by plus or minus. Plus or minus j 8.025. So by inspection, the real part is 0. Actually, there's a 0 here. Okay? So alpha, meaning the real part is 0. Beta, the natural frequency of oscillation, is actually 8.025 radians per second. Because the resulting equation will be an oscillatory motion. There is a natural frequency of oscillation. It is oscillating, and the oscillation is actually represented by beta. And actually the unit of beta is radians per second. So if we now try to bring out the equation of this, S now will be, under case number 3, hold on. I just expedite the solution. We lack space. Under case number 3, S is actually equal to e raised to alpha t times the quantity k1 cosine of beta t plus k2 sine of beta t. Okay? I shorten out. So if alpha is 0, 0 times time will be 0. So the exponent of e will be 0. So what will come out if alpha is 0, this will become 1. So actually S will just be simply this one. That is k1 cosine of beta t plus k2 sine of beta t. Right? Let's try to compute for the constant of integrations. At time t equal to 0, S is equal to minus 1/2. At the time that the block of wood is submerged, this is the water surface, the value of S is actually negative S. At time t equal to 0, S is negative 1/2. Why negative? It is below the water surface, right? It is this one. So substituting the value of t equal to 0, S equal to negative 1/2 back here, okay? The cosine thing, this will become 1, right? And the sine thing will be 0. So actually, K2, this portion here will be 0, and we can compute for K1. So K1 will be, at time t equal to 0, this should be negative 1/2. K1 times 1, or K1 is actually negative 1/2. So actually, the portion of the solution of this will become negative 1/2. Right? So the only unknown now on the equation of the motion is actually K2. So to compute for K2, at time t equal to 0, the speed of the block of wood is actually 0. So we need to differentiate this one again to apply this condition here. So if we try to differentiate this one, ds over dt will be negative 8.025 K1. Then the, what you call this, the derivative of cosine, it will be negative sine. So this is now presented by negative sine. Okay? Sine of 8.025t. The second one, it will be 8.025 K2. And the derivative of sine is plus cosine. So this is still plus. So after the so-called differentiation, try to apply the given initial condition that at time t equal to 0, ds dt will be equal to 0. Okay? So if at time t equal to 0, any sine function will become 0, right? So this will become 0. The cosine function at time t equals 0, the cosine of 0 is 1, so this will become 1. Okay? But if we try to equate ds dt equal to 0, what will come out for the value of k2 will be 0. Okay? So the resulting particular solution will just be simply this one. K2 is 0, so this part of the particular solution is missing. Meaning the resulting equation of the motion is just this. It is a cosine function. And this cosine function is represented by this graph here. At time t equal to 0, the amplitude is negative 1/2. It starts downward, right? Then it goes up, goes down, goes up, goes down, till it stops, right? So the equation S equal to negative 1/2 cosine of 8.05t is actually represented by this one here. Okay? Because whether we like or not, if we try to release the block of wood, there come a time that it will stop. So actually, the graph of that will be something like this. Right? Up, down, till it will be a horizontal line. It stops already. The amplitude already at this time here, many seconds after it was released, the amplitude will now be equal to 0. So this is the graph. So if we now try to compute for the amplitude, amplitude is the maximum travel distance as it oscillates. And if you try to bring out the equation, it is the amplitude is actually 1/2. This is 1/2. This is 1/2 initially, right? And what is the frequency? Frequency is represented by this beta here. Because beta is actually 8.025 radians per second. In terms of frequency, okay, this is 2 pi f, right? And the problem is asking for just the frequency. Beta is 8.025 equal to 2 pi, so frequency will be 8.025 divided by 2 pi. It is this, over 2 pi. And this is 1.277 cycles per second. It tried to oscillate 1.2 cycle per second. It's very fast. Okay? It's not too many cycles because you just submerge it, then release it. Not unless the force is actually continuing to be pushing that block of wood, it's a different story. But the problem is just you submerge it, then release it. So it will try to oscillate, then it stops. So the graph is something like this. Okay, that's it, guys. That's a second example of an oscillatory motion under second order differential equation. This is DE lesson number 45 under our main topic, second order differential equation application. Oscillatory motion, example number 2. Okay guys, for those who are studying and taking up engineering, you needed this one under your so-called differential equation. So if you like it, please click like. If you want to subscribe to my channel, please click subscribe. My YouTube channel is actually at youtube.com/@ProfDavidJ.Reyes. Please click subscribe. And if you want to subscribe to it, please click, no. If you want to share it to your friends, you can share it. Good evening, Los Angeles.